Hi and welcome. This time around we have another interesting project from that welding company I do some work for. They do mostly laser welding, but they've broken out into regular welding. I think this will be MIG. What they need is a fixture to help them put these guys together. Maybe you can tell what they are. I feel like I'm channeling Curtis down in Australia at this moment. I don't know why. Perhaps it's because these are brake shoe assemblies for Caterpillar heavy machinery. This is a 4-inch, this is a 5-inch, and they also have 3-inch, so I have to make a fixture that will hold this piece in place so that it can be welded. It needs to be flat and parallel, and there needs to be almost zero gap between this outside piece and this webbing right here. They call this the web. So there needs to be almost no space here, but as you can see, there's quite a bit. I think you can see anyways. So we need to make a fixture and we need to press these pieces together. So that's going to be quite a task. So I've sort of got an idea here. Here's sort of the rough idea of my fixture design. It looks really simple. So basically it is an aluminum piece that this guy sits down into with a lip back here. And I'm going to press this guy using 3 of these extremely heavy duty, I think they're about 6,000 pound lever pressing feet. I'm not sure what you'd call them. A few moments later. These are called push toggle clamps. And so this one's good for about 5,800 pounds force, holding force, which should be more than plenty, I think. I've got to be able to deform this guy, so there will be 3 of them. One will press in the middle to center this guy. This guy is located by this little pip sitting out here. So the first one will press dead center, which will press this guy into the center, and then I'll have one from this side and one from this side to deform this part so that it matches. Let's see, what else? This will be held at the height for a 5-inch brake pad, or yeah, brake pad, brake shoe. I think these are brake shoes technically, right? So these will be, this will hold this at 2.5 inches. For the smaller ones, the 4 and the 3-inch one, what I will do is this guy will be held in space for the largest one, and then the smaller ones I'll build spacers that hold the plate that the pad is actually mounted on up, so that I can handle one fixture for all 3 types of brake pads or brake shoes. I guess again these probably are brake shoes. One of the big problems with this is trying to locate on this part, number 1. Leave enough clearance so you can get a MIG welder to weld like here to here and here to here. All of that is going to be challenging. There are no good location points on this guy. Everything is really loose spec, but then they want the final part to be relatively tight spec. Also, how do you weld one side, then weld the other while keeping it in a fixture? So what I'm going to do is I'm only going to support it in the middle here, as you can see by this design. So we're going to support this guy in the middle. And that way, when I flip it 180, the part will sit also, well, the whole thing 180. The part will sit and also be supported both directions, and the toggle clamps should be able to hold this all together while you do the backside weld. I think the way it's going to work is they will do 2 or 3 or 4 tack welds on one side, flip the part over, tack weld, weld all the way around, flip it back over. You can take the part out now and weld it all the way over, something like that. I haven't worked out the welding scheme. That is actually for the professionals to do at welding. I am definitely a rank amateur. Now, the next set of difficulties, besides the fact that everything on this part is extremely loose tolerance, they show a drawing of this part individually and the whole assembly together. And guess what? These datum points, they're varied. You'll notice that this final part has this ground part here. And apparently what they do is they grind this after it's together, as well as this part over here after it's together. And so the drawings I don't even have good reference points. I don't know which ones to trust as far as using datum points on any of these positions here. So what I did opt, as I explained earlier, is I opted just to ignore everything and try and hold this in the center on the curve, which was like plus or minus 20 thousandths something like that. Maybe it's plus or minus 10 thousandths on the radius of this curve. And we're going to hold it here, and we're going to press this guy on, and hopefully that'll be good enough. The one thing that they've had problems in the past is keeping this parallel or perpendicular all the way around and equidistant from both sides. So hopefully we'll solve that, and the part will be accepted for when they finally grind it, and it'll all meet their specs for Caterpillar. So the next bit of my difficulty is that these radii are so big that they're really too big to handle in my lathe comfortably. This is like 11 and change inch diameter. I have a 14-inch throw lathe, but my largest chuck is a 10-inch chuck, which means I'd have to try and mount this to a faceplate. I do have a very large 12-inch diameter, 3-inch thick round of aluminum. That's one way to do it, and I can mount that to figure out how to mount that to the faceplate safely. The thing weighs like 40-some pounds, kind of a scary thing to be, you know, swinging around on your lathe. If it's not perfectly balanced, you probably have to go really low RPM just for safety's sake. However, I think what I'm going to try and do is I'm going to try this first. I found a scrap piece of aluminum that I might be able to make work. Let me bring you over. Give me one sec. Okay, so here's a really decent sized chunk of aluminum. It's 3 inches thick. I don't need 3 inches. I need something like a little bit over 2.5 inch, like 100 thousandths over 2.5, like 2.6 inch thick. So we're going to remove some material off there. I need the full width, and it would actually be better if it was a little bit larger, but we're going to go with what we've got. So it's not going to be quite as wide as I'd like. Here's the part. The part just barely fits edge to edge on this guy. So this top part of this radius up here meets one edge, and the other part is now on the bottom. So I need to cut a chunk of this guy out, and then I need to cut this large radius here, and then I need to do an inset portion, because if this is a little confusing, this guy will sit right here. So it needs to be inset in this radius right here. So I need to machine this outside radius, this inside radius, and then I need to do these cuts here and here. None of these really matter other than for locating this point. I'm thinking about boring or drilling a hole through this guy for a pin to go down the center here, and that will help me locate. And then I've got 4 screw holes that are going to go into this guy, 2 of which line up with my rotary table. So we're going to try and cut this outside curve and this inside curve here and this ledge with the rotary table. I know, don't laugh at me, but that's the approach I'm going to take. I planned the spacing of those holes. This is not a scale drawing. I have a scale drawing if you want to see it. I always print scale drawings just so you can see it. So I planned it so 2 of the holes, besides being able to bolt to the base plate, which is a 1-inch thick piece of tooling aluminum, also lines up with, conveniently, with 2 of the T-slots in my rotary table. And there will be actually 2 more bolts going through as well. On top of that, you can see this green here. That is a plate that will hold this guy down. So this sits on a ledge, and then another plate will fit just over the back of it here to prevent it from lifting up. It only overlaps 1/4 inch. I hope that's enough at this point. I'm trying to give as much room as possible to get their welder in there, so I tried not to do too much, but we will see. This is where we're at. So the first step is I need to cut off a chunk of this guy, and then I need to start machining it to dimension. First up, we're going to saw this piece, and you might wonder why I don't have the piece clamped down. It's because the weight and the saw blade pressing in pushes it against the fence, and they tend not to move at all. This cut's going to take a while. I watched on a video recently, the guy was saying that you take the cutting wax rather than straight in like I've always done to get it in the teeth, and you just come at the side of the blade, and that'll be more than adequate. I guess that's counting on the set of the teeth to pull the wax in. That actually seems to work. Final pass. Stock is dimensioned to thickness. Got this side square to this top and the bottom. This side I'm leaving rough because that's the side that's going to have the curve on it, so I don't care. Almost all that material is coming off. Now I just need to do both sides and square them up and get this width to the appropriate dimension. So we're going to see a lot of this beast of an end mill. This is a 3/4 inch end mill, 3-inch length of cut. And we're going to see a lot of this doing all of these round profiles. And I'm just squaring up the side and getting this to dimension. All right, we're within 1/1000th. And one thing you've got to pay attention to when you're using even solid carbide cutters like this one, when you're doing 3-inch cut or 2 and change depth of cut, there's deflection. So I don't make my measurement till I've done 4 passes back and forth, where the first one removes a lot of material, then a little bit more, well, a whole bunch less, but still a significant amount of material. And then it moves a fine amount of material on the last 2 passes and just cleans it up. And that way I'm sure that I can be repeatable. Otherwise, the deflection is seriously a problem. So next up, in order to put this, you can see the rotary table sort of underneath there. There's the T-slots in the rotary table, and that's the edge of the rotary table. We need to turn this radius and this other blue line radius here. But before that, I need to find some way to mount it to the rotary table. So there's going to be a locating pin in the middle, 1 inch. So we're going to drill that and bore that. That's going all the way through this beast of a piece here. Then I've got to drill these mounting holes, which I made the mounting holes line up so they'd also fit in the T-slots of the rotary table, and that was what will hold it down along with the pin for orientation. Then I need to drill these 3 holes and for tapping. Those holes will be for the plate that sits on top, that gets screwed down, that holds the webbing piece centered. And then there's 2 more holes that hold this to the base plate as well that need to be drilled. These are drilled and countersunk for cap screws. That's what we're going to do. So first I'm going to start with the number 7 drill here, which is the proper tap drill for these. And I'm just going to pre-drill all of these other holes with starter holes, and then we'll come back and do these other ones to size. That makes sense. Boring out the 1-inch hole. Should be the last 9/1000ths. Should put us right on. I was using an indicator on the side of the boring head to control how far out it went, so I can be much more accurate about the holes rather than using the dial there. I never trust it. It's probably good that I don't. So I got to remember I'm reading radially with the dial indicator. There's the fit on the Morse Taper 3. We're good. I might make another one of these out of hardened material, because this is just plain old cold rolled, and it gets scratched pretty easy, even though this is aluminum. But you can see little dings here that I had to stone off. So yeah, I think we're gonna have to do something about that. Here's the piece partially done. Hole is bored, and I found out what was causing me my problems, and that's because there was a chip in my carbide tooth on the boring bar, although I couldn't see it even in magnification until I went and looked further, and that's why I was scoring up the side of this. So I made it a little oversized, so I might make just a slightly larger mandrel. This one's undersized and it's not hardened material, so I'll probably make one of these instead out of hardened material and make it to size for this so that it doesn't slop around. It's unfortunate that's how it worked out, but this is not a specific diameter or anything like that. I just chose an inch because it's convenient. Right now it's, instead of 0.998, it's like 1 inch on the money. So that's not terrible, right? Okay. We have a piece of 4140 pre-hard here, and we're gonna use this as a dual purpose tool. One of it's a part of the final assembly, which will be to help distribute force on this guy. It's gonna fit in this hole and it'll help provide force distribution there. It'll also help me align this guy on the rotary table. So I've faced it off. Let's take a 50 thousandths pass. It's kind of a mediocre finish. Added some tailstock support. Switched to a Kennametal larger radius cutter rather than a positive rake one. Oh yeah, much better finish already. Look at that. I'm gonna have to part this guy off. Just remove any little tooling marks, or most of them. Only took 3 attempts, but we got there. This is no wiggle, very smooth fit. So it's a sliding fit, but absolutely no wiggle, even way out here, which is, oh, there's a tiny bit right there. But really good. That will work for me. So we need to part this guy off. I made it 1,000th undersized, so that's why it's as much of a loose fit as it is. Okay, got the right dimensions, so we can part this guy off. Trying to see how little a nib I can get. It's going to break on its own. There it goes. It's actually pretty small. You can barely see that nib. All right. Just going to manually tap. This is hardened material, so it's a little challenging, but it's going pretty nicely. These fine pitch threads make it easier because they're not as deep, so not as much force is required. All righty. Okay, the face on this guy is ground, so hopefully that'll get it so it's parallel, this face parallel to this face, and that should be the case. So I think we're good to go. So now we've got our pin. The threads we obviously won't need when we use this as a pin on the plate, but that's okay. All right, so let's give you a rough feel what's going on here. So I still need to remove this material here, this material here, and here, and here. I'm gonna wait to do that on the rotary table, because right now, all of these other holes, including that 1-inch hole, are centered exactly about these sides here, so that's essential. And the only part that comes in contact, I could actually bandsaw these out and leave them rough because it doesn't matter at all. This part here only contacts where the blue line is, and I don't have it centered quite properly, but sits something like this here. And then it's got to flip 180 and hit the other side. Now they've got a compound angle right here, so I might actually have to remove some material that supports right there as well on both sides. I don't know why they chose to do that, but it makes it particularly challenging. They've got a standard radius from like here to here, and then there's another just different angle right here, a different circle radius, much larger, I think. I'm not sure, but the drawings unfortunately don't help because they don't give, you can't find the center of those circles very easily. They don't give you enough information on the drawings to find them. So anyways, that's how it's going to sit. This part will first go this way, then the whole assembly will flip over this way, and it'll be pressed up against where that blue line is there with this edge here, which is Nasty Bird. So that's going to also be interesting. Anyways, that's kind of the plan. So I'm going to wait till I hit the rotary table before I think about removing this material here, this excess on the side. And of course, the curve we're going to do on the rotary table. Then we're going to remove this material also on the rotary table. That goes down like, well, not quite a quarter inch. This is 200 thousandths roughly. And that's it.